All right, I think it's working. Yeah. Okay, so today I'm going to talk about how I did the data analysis for our DORGE paper. And this is my R markdown file called dorge.rmd. I just first opened it with RStudio. And this is the title which are needed for compiling a PDF or HTML file from this code. And this is just some necessary things to optimize the look. And so this is a fresh environment. And what I'm going to do is that I'm going to first set a session to the working directory to the source file. So I'm in that folder. And then I run this chunk first. And then I need to load the R packages I used. So this piece of code is just to make sure that if the user didn't have the R package installed, it can be installed automatically. So in other words, the user will not run into an error message if the package is not there yet, because this installation will happen. Okay, so the GLNet package is to be used for running Lasso, Ridge, and ElasticNet regression. They're all in this package. And this random forest package is for implementing the random forest classifier. And this E1071 is for running support vector machine. And this neural net is for running neural networks. And this XGBoost is for running XGBoost. And ggplot2, gplots, and lattice, they're all for visualization. So in particular, I'm going to use the level plot function in lattice so we can get a heat map, which looks pretty nice. I'm going to show that. And this facto extra is for some nice visualization of PCA results. So I use this package for that purpose. And PRROC is for plotting precision recall curves or ROC curves, and also for calculating the area under the curve. So I'm going to use that. And this MPROC is a package from my previous work for implementing the Neyman-Pearson classification. Okay. And this parallel is a built-in package for implementing parallel computing. So after this, I have all the packages loaded. Okay, now there are some functions I'm going to use for this analysis. The first function is mporderstat, which is a function I wrote to implement the Neyman-Pearson classification. So although that I used this package already, but then I figured out that what I really need for this analysis is not fully implemented in the package. So that's why I wrote some functions for that purpose myself. And in particular, this mporderstat function is a function that's needed for this NP logistic regression, ElasticNet. So LR stands for logistic regression, ENet stands for ElasticNet. So I wrote an NP function for implementing ElasticNet with logistic regression as the model for my data. So you can see that in this function, I basically called this mporderstat right here. So that's why I put that function outside. And for this function, I will need to provide X, which is my design matrix containing the features, and Y, which is the binary response. Alpha is our targeted type 1 error in the Neyman-Pearson classification. And delta is the tolerance level for violation rate. I set it to 0.05 by default. And lambda is the lambda for ElasticNet. And B is the number of random splits to implement Neyman-Pearson classification. And this is a random seed. So I have all of this for implementing this function. So you know, a nice functionality in RStudio is that I can always fold this function so it becomes much shorter, and then I can run this one. And I also wrote a function for logistic regression without any penalization. All right. So these are all the preparations for functions. And now data pre-processing. I obtained 2 files from Dr. Jie Li, the first author of the DORGE paper. The first file is a data file containing all the features and observations. So I'm going to read this file in. And please note that here I use the string as factor equal to false, so I can make sure that R will not automatically turn some integer features into factors, because that will cause some troubles in my analysis. And the header equal to true means that the first row in the CSV file will be treated as feature names as opposed to feature values. So after I reading this data, I can take a look at its dimension. So you see that I have 19,636 rows and 76 columns. And I'm going to examine the column names. So you see that these are the column names. Those are mostly features except the first one. So if I scroll up to the first one, and this is called gene, and this is the gene name, but this gene name is not a feature. So then what I did is that I will assign the first column to a vector called genes, and then I'm going to use the remaining 75 columns as a data matrix. So this will be my data. And now I assign this matrix with column, with row names, same as genes. So now the genes are no longer a column, but just the row names. All right, that's how I process the data. Another file I got from Jet is this genes.new file. And I will first read in it. And let me take a look at its first few rows. Then we can see what it has. So this is the file. We can see the first column is also containing genes, and those genes correspond to the same genes in this file. And the columns are regarding which of those genes are known TSG. So here in the background, the TSG stands for tumor suppressor gene, and OG stands for oncogene. And neutral genes are those that are neither tumor suppressor genes or oncogenes. And after talking to Jen, I learned that I need to use the last 3 columns. So I should use the neutral genes as the negative set. And for predicting TSG, I need to use this column, TSG.all.set, as the positive set. And for predicting OG, I need to use OG.all.set as the positive set. So in other words, I'm going to have 2 training data sets, one for TSG, one for OG. And this is what I did. So you see that I'm trying to assign the column, this one, into neutral genes. So what I did is that I grabbed the genes whose value is equal to 1 as the neutral gene set. And I'm going to use this second to the last column to get the TSGs, and then the last column for the OGs. So I will have 3 sets of genes. And after talk to Dr. Wei Li at JET, we learned that we do not want to use the overlapping TSG and OGs for training, because those genes are not very clear. I would say not very clear for us to define classifiers, and may make our 2 classifiers, one for TSG, one for OG, overlap too much. So for that consideration, we decided to remove those overlapping genes, which is called dual functional genes, from TSG training set and OG training set. So this functions to obtain the intersection. And after I obtain the dual functional genes, I just use the set difference to remove them from TSGs and from OGs. Okay, now with all the pre-processing, I obtained a data matrix, 4 sets of genes, NGs, TSGs, OGs, and DGs, dual functional genes. And I'm going to save all of them to an R data. So the reason of doing that is because then I don't need to run this chunk again if I want to reproduce my results. So for a new user, they can start from here. They can start from the R data to load it to the R space. And I'm going to do that. Now with the pre-processed data, the first step is try to explore interesting patterns among them. So my first idea is to look at the feature correlations. So I use this core function to obtain pairwise correlations between those 75 features. So I obtain a 75 by 75 correlation matrix, and we can check that. That's it. And then I used level plot to plot those features, use their original orders. So I didn't change the order provided by Jeb, but just use the order 1 to 75 in his original file to plot the features. And this argument is trying to rotate the x-axis labels as vertically, so we can see that it's nicer. And this CX argument is just to reduce the labels so they do not overlap with each other. And I also use another function, heatmap.to, to plot the same matrix again. And the purpose of doing that is heatmap.to can organize the rows and columns by hierarchical clustering, so I can see which features are more highly correlated with each other. So by seeing the original order and this reordered by hierarchical clustering, I can get a better sense about the correlation structure. And here this trace equals to none means that I try to remove the trace in the heat map, which to me is not very easy to see. Okay, so let's look at the plot I generated. So I'm not going to rerun this because it's already saved. So it's here, feature correlation. And you can see that this is the level plot output. So this is the original order. And what I really pay attention to is those blocks with very high correlation. So for example, let's zoom in a little bit. So clearly you see this block shows very strong correlation between two features, and they correspond to missense damaging benign ratio and missense benign ratio. By just looking at the names, you can see, oh, they should be similar. And that's why they have very high correlation. And if we look at this one, it's also reasonable. Those three features correspond to log total number of splicing mutations, log total number loss of function mutations, log total number missense mutations. So because these features were manually constructed and curated by Jen, and it's not surprising that some of them are highly correlated. And also this huge block here, if you look at this block and moving to the left side, we see they are all corresponding to those epigenetic features, which is the contribution of the DORGE paper, because we, for the first time, incorporated those epigenetic features for predicting cancer driver genes. Okay, this is the original order. Now I'm going to switch to the hierarchical clustering result. Now in this figure, the brighter the color, the stronger the correlation. And we can actually see that this bright block, if I go to the right, they are still corresponding to those epigenetic features. So they are, yeah, after hierarchical clustering, they stay as a block. And this one, if we take a look, they're all corresponding to some sorts of missense mutations. And this one is loss of function mutations. This is corresponding to splice variant. So we see that these correlations are not unreasonable, and but the most important information we get from these two figures is that we need to account for the correlation structure when we try to interpret the model classification results. Okay, so this is the exploration of the the feature correlations. Now I'm going to do another exploration using dimension relative reduction by PCA. So I want to see on my data set, if I look at the training genes with known labels, TSGs, OGs, and NGs, how are they separated in PC space? This can give me an idea about how easy or how difficult the analysis task is. So for this purpose, I created two data sets, one that only contains the training NGs and training TSGs, and another that only contains the training NGs and the training OGs. Okay, so I first do PCA on each training data and also on the whole data. So the whole data means that if I obtain the projection, not just using the training data, but using all genes, what would happen? And so the function I'm using for PCA is called PRComp, and this is a built-in function in the R, I think loaded in R. Okay, so we can run those three. And one more thing, the scale was set to true. So which means that I asked the PRComp function to scale the data matrix so that every feature has mean 0 and variance 1 before they do PCA. Okay, I run those three things, and then I'm going to visualize the PC result. So those two functions, fviz and fviz var, are from the package I mentioned for visualization of PCE results. And furthermore, I will show how the data points look like in the first two PCs in PC1 versus PC3 and PC2 versus PC3. So I'm going to go to the plot and show the result. So the first one is to show the contribution percentage of variance explained by each PC. So we can see clearly that PC1 is the dominant one, explain more than 20% of the total variance. PC2 explain about 9% of total variance, and these two explain much more than the rest of PC, and this is for predicting TSG. Okay, and this plot shows the contribution of each original feature to the PC, or we can say this is a loading figure. So what's clear here is that those loss of function mutations and also those missense, so those mutation related features are contributing most to PC1. While if we look at PC2, the most dominant features are those epigenetic features. So this shows something very interestingly. From this figure, we can already see that our DORGE idea of incorporating epigenetic features into the classification seems reasonable from this figure, because they are definitely contributing some orthogonal information in addition to those mutational features, which were used by previous papers. Okay, this is the dimensionality reduction glance. And now let's look at the data points or the genes where they're located. So we can take a look at this PC1 versus PC2. Every dot represents a gene. And we can see that the black ones are NGs, the red ones are TSGs. So what's clear here is that the TSGs tend to have smaller values in PC1 and smaller values in PC2. So going back to this figure, you see this mutational features are negatively correlated with PC1 because they are having negative loadings, while the epigenetic features have negative loadings in PC2. So what this will tell us is that if TSGs have negative PC1 and negative PC2, then we will learn that TSGs have high mutation rates and also high epigenetic signals. And this is actually consistent with what we know of. So this result seems reasonable. And so I'm not going to talk much about PC3 because I think PC1 and PC2 already shows a very good separation for TSGs. Now, OGs. So this is on the OG training data. Again, we see PC1 clearly dominates. And if we look at the loading plot, again, the mutations are contributing to PC1, epigenetic features contributing to PC2. And this is the scatter plot. We see that the separation between OGs and NGs is not as good as that for TSGs. However, if we look at this figure, we can still see PC2 seems to be a good dimension because the OGs tend to have very large PC2 values. And here, if we look at PC2, these are the PC2 contributing by epigenetic features, and epigenetic features are negatively correlated with PC2. So this would actually suggest that probably those genes are actually having small or low epigenetic signals, but we will not actually examine this further because now it's not as clear as that for TSG. Okay, and now all genes. So we don't use any training information, but just look at the whole data set, the dimensional analytic reduction. And PC1 and PC2 are still dominating. And looking at the loadings, similar. So now we see the PC1 is still contributed by the mutations, PC2 by epigenetics. So not much different from the training data loadings. And this is a plot showing all genes. Now I'm using 4 colors, the NGs in black, TSGs in red, OGs in green, and other genes, which means they're none of the above 3 in blue. So one thing I can see is that because there are so many genes, I use very small dots and use transparency so we can see the overlap. So one clear thing we can see is that the OGs and TSGs are actually together. They are not very well separated in PC, but they are clearly separated from the NGs and other genes. So based on this plot, if I'm zooming a little bit, you can see that in this case, it's possible that some of the others may be classified as NGs and, as TSGs or OGs. And that's what we want because the goal of DORGE is to uncover some novel cancer driver genes that are not known as TSGs or OGs. So given that we see some blue dots close to those red and green ones, it seems that our goal is not too ambitious. We can probably recover some new genes. Okay, these are all what I learned from PCA. It's just an exploration of my data so I can get a better sense of what the data look like and before I do any detailed analysis. All right, so I'm going to skip those codes because those are just used to generate the plots we just saw. And that's the exploration. Now I'm going to really tackle the task of classification. So the goal is that we're going to use the training data based on known NGs versus TSGs to predict TSGs based on from all the other genes. I'm also going to train another classifier based on known NGs and OGs so I can predict whether other genes are likely OGs. So I'm going to do 2 separate predictions. And before I do that, one issue I need to deal with is that my training data is heavily imbalanced. So if we take a look at the number of NGs, it's about 4,000 genes. But if we look at TSGs, only 200, and OGs, 200. So it seems that my NGs, which is one class, I will call that class 0. And for the TSG, I will call class 1. So if we look at the class ratio, it's totally unbalanced, right? So this is so much more than this number. And we know that in classification, there's such an imbalance may make our classification not very accurate because if we use the overall classification error as our criterion, we would tend to predict every gene as NG because that will not make the error to be too big since may seem this minor class is not hurting too much. And that's the issue we're going to address. To address that issue, I use 2 strategies. The first strategy is that I try to balance those 2 classes by downsampling this large class 0. So the strategy I use is I will specify a fold. So this fold is my desired ratio in this R. So what I mean is that if I set R equal to 1, I will downsample NG to be equal to TSG. I will also set R to be 5, so the NG will be equal to 5-fold of TSG. So what I did is I tried 3 ways. One is to keep the original ratio. The other is to downsample NG so the ratio becomes 5:1. And another one is to downsample R equal to 1, so NG equals to TSG number. So I use 3 ways to train classifiers and compare the performance. And this function is just try to do the downsampling. So I wrote this function because I need downsampling for every task, as you will see. And so for that purpose, this function just serves the general purpose. And the one thing I want to point out is that after I downsample, let's say NG equal to TSG, I can have many partitions of NG, right? So if I say I divide this 4,000 by 242, I can have multiple NGs, and I will keep those multiple partitions of NGs, and I'll keep those partitions so that each partition will be used to train with TSG. And let's say I can divide NG into, say, 15 folds. That's the number of folds here, number of partitions. Then I will use each partition to train with TSG, and then I will average my resulting classifiers. So doing so would make sure that I didn't waste my NGs. If I just use a small subset of it, the other NGs will never be used, and I think that's a loss of information. So by downsampling, I will basically create multiple training data sets based on multiple partitions of NGs. That's this function. Okay, now I'm going to create my training data. So this is from what I created before, this matrix containing only the known TSGs and OGs. And this is my design matrix or feature matrix. I also create a corresponding binary response matrix. Number of zeros equals to number of NGs, the number of ones equal to the number of TSGs. And I decided to use 5-fold cross-validation to choose a classification algorithm and to choose the sample size ratio. So as I said, I will consider 3 ratios, 1:1, 5:1, and the original ratio. So this K means the 5-fold cross-validation. And to make sure that my results are reproducible, I will create my cross-validation data partition in the beginning. So I will divide my data into training and test data all before I run any algorithms. So I can make sure that all the algorithms are based on the same data partition. Okay, so this is to show how I'm going to divide my number of genes into K folds. So I use the sample function to randomly draw a fold index for every gene. So every gene will receive a label from 1 to K, means that which fold this gene is going to be assigned to. And I'm also going to create a downsample index for my ratio 5:1 and my ratio 1:1 for my analysis. So specifically, I use this loop to create my cross-validation downsamples. So you see what I did is that after I obtained the cross-validation index here, for each fold, I will obtain the test data as the genes with that label, and the remaining data points are the training data. I have the training X, training Y. And then what I did is that I downsampled the training data based on the ratio I desire. So basically this list will store the index of the downsample. For example, if I will partition this training data inside the training data, I will partition class 0 into 10 folds. I will store all the 10 folds here. So I know that based on this ratio, I will have 10 folds of class 0 to be paired with 1 fold of class 1. So I can use every fold for training. And also for the ratio 1:1, I did something similar. But this is just to store the data partition. So I don't need to do the partition once again when I run the algorithm. The data is already partitioned. Now this is the key part. How do I train an algorithm? I'm going to use logistic regression to start with, and I'm going to perform cross-validation. So since my data is already partitioned, I'm going to obtain the test data, training data, and I store them as X train, X test, Y train, Y test. And because the GLM function in R is what I'm going to use for logistic regression, and the GLM requires the data to be input as a data matrix, or I would say data frame. And so basically, I first convert X train to data train, and then I added a column for Y. So they are all called data train. X and Y are together. And I run this command. And the key is that I set the family to be binomial. So I'm doing logistic regression, not linear regression. And after I train the model on training data, I'm going to apply it to the test data to predict the probability of each gene in the test data for being a TSG. So I'm going to use this command. It will take the model into input, new data, and also we need to specify this type equals response. This is important because if we go to the R function menu, if I go to this, we can see that in the argument, there's a type. If I don't specify type equals response, the default will be link, and the link is not what we want. The link will give me the fitted linear function, but what I really want is the fitted probability. So you see here it says type equals response gives the predicted probabilities. So that's why I use this argument. And then given the probabilities, they're all between 0 and 1. And closer to 1 means that a gene is predicted to be likely TSG. I'm going to use this to get the area under the precision recall curve. And you can see that I didn't use the classification error as my evaluation criteria. The reason is because I know my prediction is unbalanced. There will be much fewer TSGs than NGs. Therefore, overall classification error is not a good measure, but precision recall curve balances that class ratio. So that's what I really want. So I decided to use its area under the precision curve as the criteria. The larger the area, the better. So I'm using this function in the PRROC package. This is called PR.curve. Okay, this one is nice because you can simply input your predicted probabilities and the real labels in the test data. So you see, I'm using this, the score.class0. It says that it can be the classification scores of 1, all data points, or 2, only the data points belonging to the positive class. And I'm using the case 1. So it says in the first case, score.class1 should not be assigned an explicit value. So you see, I'm not assigning that argument, but left at default. In addition, weights.class0 needs to contain the class labels of the data points. And 1 for positive class, 0 for negative class. And that's what I did. So I put the class labels as the weights.class0. And it says accordingly, weights.class1 should be left at default value. So I didn't specify it. And I'm using the output called AUC.integral. That will give me the area under the precision recall curve. And that's my criterion. Okay, that's for the original sample ratio. Now I'm going to use the downsample 5-to-1. And specifically what I did, I'll try to explain it as clearly as possible, is that I first calculate how many folds can I divide class 0 in my training data based on the training class 1. So after having that, I'm going to calculate the precision recall curve area as follows. So for each of the class 0 training fold, what I did is that I obtained the corresponding class 0 data and put it together with the class 1 training data. And then I create the corresponding binary response vector. Then I apply the GLM. Then I apply the GLM, trained GLM to the test data. The test data stays the same. And I would obtain a predicted probability vector based on this one partition, this ith partition. And I go to the next partition of my training data, 0, and I obtain another predicted vector, predicted probability vector. So doing so, I would obtain a total of non-folds probability vectors. And then what I did is that I would perform averaging to obtain the mean predicted probabilities by averaging over all the folds of my class 0. So using this function to get average. And more specifically, I want to say that this MC apply is to use parallel computing, because you see, go down here, I can have this number of cores equals the number of cores on my computer minus 1. So this minus 1 is to just save one core for my background, and I will use the remaining cores for this computing. And this MC apply will retain a list type. I'm going to unlist it, put the values into a matrix, and each matrix, this matrix will have each column corresponds to one set of probabilities based on one partition. And then I'm going to take the average across the columns for every row. That will be the average predicted probability for every gene. And with this average predicted probability, I'm going to use it as the probability for my precision recall calculation, and I will get area under the precision recall curve. And for the ratio 1:1, I did everything exactly the same, just changing the ratio from 5:1 to 1:1. Okay, so that's all for this part. And then I'm going to return 3 areas under the curve. One for the original ratio, one for the 5:1 ratio, one for the 1:1 ratio. And let's look at the results. So I'm going to run everything in this chunk, so we don't miss anything. I think I should start from here. So let's wait a little bit so we can see the results. Right, so this is the result. Based on the original ratio, the area under the precision recall curve is 0.7877. This 5:1 ratio, 0.7808. 1:1 ratio, 0.6895. So there's no advantage of balancing the ratios. It seems that based on the precision recall criteria, the original ratio works pretty well. And one thing we also noticed that there are some warning messages. This message just told us that the logistic regression actually has a perfect separation of class 0 and class 1. And this is usually not desirable for logistic regression, because if there's a perfect separation, we cannot really estimate the linear boundaries well. So this message also gave us some indication that we may consider some penalization to help us address this issue. So that's why we move next to logistic regression with lasso penalization. So for lasso penalization, one thing we need to choose is the penalization parameter lambda. How should we choose the lambda? And this one, I'm using the cv.geomnet, which is the built-in cross-validation function in the geomnet package. Let's take a look at the menu. So in this cross-validation function, what I need to specify is the family, which is binomial. So telling this function I'm using binomial family, it will perform logistic regression. And this is important. Another thing is that the GLNF function requires the feature matrix to be matrix as opposed to data frame. So I'm going to convert the data frame to matrix, and the response needs to be a factor. So I'm converting this numerical 0, 1 vector to a factor. And I want to choose the lambda that minimizes the overall loss or the cross-validation loss. And for this one thing I want to say is that the default is that the logistic regression is using the deviance as the measure for error instead of the MSE. So it depends on what type of family you use. For binomial, we will use deviance. And for the output, if I scroll down, you can see that lambda min is the value of lambda that gives the minimum CVM. And CVM is what? It's the mean cross-validated error. So in this case, it's my mean cross-validated deviance. So I'm going to use this to select my lambda for lasso using the whole data set, the whole training data set. So let's take a look. So this will take a little time to run. Okay, and then I'm going to use the same lambda as opposed to choosing lambda in my each time running lasso. I think that can save a lot of time. So this is the lambda chosen, which is pretty small, which means that we don't need too much penalization. This is quite expected because our feature number is not big, only 75. Okay, now I'm going to use this cross-validation based on precision recall curve area as the criterion. So everything is the same as what I did for logistic regression, except that I'm changing the GLM function to GLMnet function. And one key difference is that when we use the GLMnet function, when we predict the trained model on test data, this is a parameter or argument we must specify, that is the type. So I'm choosing response here. If we don't do that, it will give us some trouble. So if we go here and see that the default is link, so it will not give you the predicted probabilities by default. So you have to specify to be response, same as in GLM. And also you need to give them the lambda value you want to use for the prediction. And then I just use the pr.curve function again. So this part is not different from the previous one, so I'm going to continue. And then I use the ridge regression with logistic regression, of course. So here, the key difference between ridge and lasso is that I set this parameter lambda to 0 because default lambda is set to 1, which means I'm doing lasso, and 0 means I'm doing ridge. And if I go further down to ElasticNet, I will set lambda to 0.5, which means I have half ridge, half lasso. So other arguments are all the same because we're using the same GLMnet package. So this is not different from the lasso case, and the results are also showing in the same format. I'm going to show the results in the Excel file later, so we don't need to run every code one by one. Okay, this is ElasticNet random forest. So this is a different method because random forest is a tree-based classifier. It's not a linear model-based. It's not a generalized linear model-based. So I'm using the package, and one tricky thing is here. So how do I obtain the predicted probabilities? I need to go through this set of rows, the codes. So it's not very obvious from the beginning. Let's look at the function, random forest. So if we go down, look at its output value. So it will give you those output. And since I already input test data here, so I will get an output called test. So it says if test set is given through the xtest argument, this component is a list which contains the corresponding predicted error rate, confusion, votes for classification, or predicted MSE and RSQ for regression. So we are in this case, we are in classification case. And so previously, in my first try, I used the predicted as the probability, but that's wrong because the predicted will be just 0 and 1. It will be the predicted labels, not the probabilities. To get the probabilities, I need to go to the votes, and the votes will be a 2-column matrix where the first column corresponds to the predicted probability of being class 0, while the second column is the probability for class 1, and each row add up to 1. So the two probabilities in one row add up to 1. So I will use the second column as the predicted probabilities for class 1 for my calculation of precision recall curve. That's just the thing I want to talk about. And then I did this for ratio 5:1, 1:1, same as before. Okay, next method, support vector machine. So for support vector machine, one thing I noticed is that they require the feature matrix to be scaled. So I did the scaling outside of the function. I scaled every feature to have mean 0 and variance 1 before I run support vector machine. And one thing, I'm going to run this line, one thing to mention is that in support vector machine, in order to get the predicted probabilities, I need to add this argument, probability equal to true. And here I'm going to show, or I'm going to try the linear kernel, because I know the support vector machine with linear kernel should be similar to logistic regression. So that's why I'm going to use this as a sanity check. So I use the linear kernel, set the probability, and one tricky thing is how do I obtain the predicted probabilities? So let's look at this predict.svm. So going down here, it says that I need to specify the probability to true so I can get the probabilities, but this is not enough. So basically, we would need this thing. So the value, okay, so the value output from this predicted.svm is a vector of predicted values. However, this is not really the probabilities. Again, it's just a 0-1 prediction. So to obtain the probabilities, it says that we would need the, let me see here. And I think I need to, so basically it says that there's a attribute. So there, the vector will get an attribute, and the attribute will, the vector, that, okay, if probability is true, the vector gets a probabilities attribute containing an n by k matrix, n number of predicted values, k number of classes of the class probabilities. So I then figure out that to obtain that, I need to use this object as an input into the attribute function and then get the probabilities, and it will be an n by 2 matrix corresponding to my 2 classes, and the second column will be the probabilities for class 1. Okay, then I get the probabilities, and then I use the PR curve to obtain the AUPRC. And that's for support vector machine with linear kernel, and also I try the Gaussian kernel. The Gaussian kernel is the default, so I don't need to specify it. So next method is XGBoost. So XGBoost is a very popular method right now, so I'm going to try it. And two key parameters to tune is the maximum depth, because it's also a tree-based method, and also the number of rounds for boosting. So those two parameters have no clear way for choosing. So I just played with different parameters values by myself, but I have to admit, I didn't spend quite much time to investigate the best way to tune those parameters. So I just roughly tune it and try it. And then because I feel like if we do not see a clear improvement of XGBoost over those linear classifiers, we do not have a strong justification of using those XGBoost, because the method is much more like a black box compared to linear methods. So that's it. So I just tried it, and that's it. And for neural networks, actually I used to put it here, but I removed it because I think, but this based on some very quick trial, I didn't see it has any advantages. So I decided not to include it. So that's all I did for the TSGs. Now for the OGs, I tried the same methods again, and I also tested their performance using the cross-validation plus the AUPRC. So after all, I finished the section, and I'm going to show you the results. This is in my tables. So this is called a PRAUC file. So if I open it, this is how I saved all the results. And in Excel, I still can color the cells by the values. So here, the brighter the color, the higher the value, the darker the color, the lower the value. And so looking at this table, we can see that for TSGs, we are basically having ridge regression, having the best performance. Okay, this is the ridge regression, but the lasso ridge and elastic net have very similar performance. And looking at the 3 sample size ratios, it seems that we should keep the original ratio. That's for the TSG. And also an AUPRC of more than 0.8 is actually pretty good. And for the OG classification, the accuracy becomes lower. And we actually got a sense about this from the PCA plot. We already saw that the separation is not as clear for OGs from NGs than TSGs from NGs. So it's not surprising. And again here, we see those 3 linear methods are performing very well. And here, ElasticNet has the best performance. Okay, so this gives us some idea about the method choice, and we are pretty much determined that we will use the linear classifiers for their simplicity as well as interpretability for our DORGE paper. Now, we come back to RStudio, and next section, I'm going to perform classification. So I will scroll down. Okay, so based on the above results, let's first try to use Log.GS regression to train a classifier. Now, for this training, I don't need cross-validation anymore. I just need to use my whole training data to train a classifier and apply it to my whole data set for predicting genes labels. So this is my training data. This is the classifier. This is the prediction. Okay, this is for TSG. And again, we got this ordering. So it means that we got perfect separation. And for OG. Oops. So I think I have some issue here, data.org OG. Okay, sorry, I forgot to run one line of code when I was explaining. So let me fold everything so that's quicker. Okay, I think it's these 2 lines. Okay, so now I can fold this whole section, this whole chunk. Okay, now I'm at here and I need to rerun this line. Okay, I also got some perfect fitting. And I'm going to visualize the predicted results. So first of all, I'm going to show a histogram of all the TSG predictions. I want to see how the predicted probabilities are distributed and also the OG predictions. And later, I'm going to show how the known TSGs and OGs look like based on my prediction. So I'm going to go to this figure. So this is the figure I generated. So these 2 histograms show that the TSG predicted probabilities are concentrated around 0 and 1. This is good, right? Because it means that we are pretty certain that many of them are not TSG, only a small proportion of them are TSG, and similar for OG. And I'm plotting for all genes, their TSG predicted probabilities versus OG probabilities. So you see that the majority of them are near the origin, which means they're neither. And a few of them are in this corner or this corner, which means they are TSG only or OG only. And this means they're predicted to be both. And so I used to have this jittering version, so I can separate the points a little bit to make sure I do not have too many overlap at one place, but it doesn't change much. Okay, so which means that we have pretty good separation here. Now I'm looking at the known TSGs, OGs, and NGs in my training data. So you see for my training NG, most of them are close to 0. A few of them are having large OG value, OG probabilities, or TSG probabilities. And TSGs, they are mostly underlying in the right corner. So underlying the diagonal line, which means they're good, right? So we know they're TSGs, so they should receive large TSG probabilities. But we see that some of them still receive small probabilities, which means that our classification is not perfect, but that's normal. We can not easily do perfect classification. And for OGs, the majority of them are above the diagonal, which means that they have received large OG probabilities. That is nice. So logistic regression seems to be doing a reasonable job. And now let's switch back to the RStudio and try Ridge. So to try Ridge, the idea is that we want to see whether or how shrinkage can help us with the prediction. And here I wrote a function to process the coefficient estimates output by the GLMAT function. So GLMAT as a linear regression function, it will give us coefficients of the features, the 75 features. And I just want to use this function to reorganize the format a little bit so it looks prettier and we can save this to Excel file. So I wrote this function for that purpose. And now I'm going to do ridge regression for the whole training data and then predict for the whole data. So one thing I want to say is that after I obtain this prediction, okay, right here, I'm going to use this. I'm sorry, not going to use that. I'm going to use the train classifier here to grab its coefficients and process the format and save it to a CSV file. Okay, so I'm going to run these lines. Okay, and meanwhile, we can take a look at the CSV file, which is right here. It's called the TSG selected. TSG selected LR Ridge. It's this one. So open this file and then we can take a look. So I use my function to order those features from the one that has the largest absolute coefficient to one that has the smallest absolute coefficient. So we can examine the feature importance using this way. And clearly you see that what stands out is the splice total ratio and in-frame indel fraction and all the other things. And super enhancer also stands out as the percentage. But we'll revisit the feature importance later. This is just for a first check. All right, so this is what I did for the TSG. And then for the OG prediction, I did the same thing. And then I'm going to visualize the results as I did for the logistic regression. So switching back to plots, now let's look at the ridge. So in the ridge figure, we have similar histograms for the TSG and OG predicted probabilities. And this is the OG probabilities versus TSG probabilities. Still, a lot of them are in the two corners, which are good. And looking at this training genes for better visualization. So we see that we still have very similar patterns as we got for logistic regression, right? So TSGs are in this corner, OGs are in this corner. And I'm next going to try Lasso and ElastiNet to further confirm that ElastiNet is a reasonable approach. And my rationale is that if all of them give us similar results, I would opt for ElastiNet because first of all, we saw it has the best performance in terms of PRAUC. And second, ElastiNet has the advantage of shrinking some feature coefficients to exactly 0 because it's part of Lasso. And that can give us better interpretability in terms of what features are important for the classification. Okay, so I'm just going to run those codes in case I need them later. So I'm going to run this and I'm going to run this and I'm going to look at the visualization Lasso. So yeah, you see, similar, right? Not much difference from what we saw from this logistic regression and ridge. So they give us pretty similar and consistent results, which is good. And finally, I'm going to run ElasticNet. So after seeing all of those, we can now expect that ElasticNet should give me similar results. And in terms of the predicted probabilities. So you see that I'm trying to make a trade-off between the prediction as well as the interpretation. So if we have similar predicted probabilities, we want to choose fewer features for our interpretation. And let's look at the ElasticNet. So these are the histograms, all genes, training genes. So still similar to what we saw. Okay, so now let's switch back here. And I said I decided to use ElasticNet for prediction. So first of all, what I did is that I need to assign every gene a predicted probability. I already did that, but I'm now reformatting my output into a nicer data frame and write it to a CSV. So Lijie can further process this result for his visualization, for plotting for the paper. And okay, so this is what I did for saving the output. And one more thing is that we want to decide where to set a threshold on the predicted probabilities, right? That will determine how we call some genes as TSGs, others not. So how to set a threshold is a tricky thing. And if you look at this predicted probability, this is what we saw, right? We can cut anywhere in the middle, but where to set a threshold? For this purpose, I decided to first examine how different thresholds give me different number of TSGs. And I'm also going to compare with the training TSGs to see how much we covered. So I'm going to run this for loop. So you see that in this for loop, I had some output to basically to print to my screen about the messages. So I'm going to run this. Oops, sorry, I forgot to run this line. Okay, so you see, this is what I got. For each threshold, my code will output the number of TSGs I predict and the number of TSGs that overlap with training TSG. And the percentage of training TSG that I recovered, which is the recall. And I also calculate the number of correctly predicted NGs and the number of a percentage of NGs I recall. So you see that these things will help me decide where to set the threshold. And also I consulted Dr. Wei Li and Jie regarding their opinions about an appropriate number for TSGs. So you see, by increasing the threshold, the number of predicted TSGs go from 3,000 to 2,800 to 2,500 down to 1,900, and then further down and down and down. And the fewer we predict, of course, the recall of TSG would go down. That's not surprising, but we have to set a threshold. Okay, so seeing that, we can also plot things. Let me try to show you here. So these two plots shows as the threshold goes up, how the recall rate of my TSG would change, and whether the recall rate shows a clear jump somewhere. So we see that there is a clear jump, and also the smallest jump, maybe by that. So we see whether there's a plateau somewhere. We see that the smallest change occurs at threshold 0.5, and that's right here. So I originally thought maybe we can use this to set a threshold, but if we take a look at the results, threshold equal to 0.05 gave us 1,200 genes. And Dr. Wei Li and Dr. Jie Lu think that this might be too many. So that's why I gave up on this idea. But this was my first try. And I keep everything I did in this file. And for OG, I did something similar. And also I plot a histogram like this. We saw this already. And I also calculated varying thresholds and their effects on the number of OGs predicted. But for OG, you see the plateau is not as obvious. If we choose this one, the threshold would be too low and we'll be predicting too many OGs. Okay, so then my next idea is to use the MP classification to decide the threshold based on a threshold on type 1 error. That is, we do not want to mispredict NGs as TSGs under a high probability. So this probability is set to be 0.001, which is equivalent to 0.1% false positive rate. So I want to use this to guide the threshold choice using my MP classification. So essentially, what I did is that I'm using the function I showed you in the beginning, the one I wrote for implementing MP classification on the data. And also this means that I did multiple random splits, and every split will give me one threshold, and I want to average out the threshold so that I can just obtain one threshold for my TSG prediction. And let's take a look. So this will take a little time to run. And also, sorry, I think I should say that here the alpha is set to be 0.01, and here the alpha is set to be 0.005. And I tried both, so I should actually delete this line. It should be alpha. This was some old writing. So this is for 0.05. I'm going to run that, and they will give me two thresholds on the TSG prediction probabilities. So let's take a look at their values. This is the threshold, 0.64, and this is the value, 0.82. So we actually look at both thresholds and see how many genes they give us. So you see, using the first threshold, we get about 900 TSGs, and this is the recall we get from training, based on training data. Another higher threshold give me 500 genes, and this is the recall. So after some discussion, I think we would decide to choose between one of the two things. And before going to that, I'm going to repeat the same thing for OGs. I use MP classification with two targeted false positive rates to choose thresholds. Okay, and we see that if we use 0.01, we get 691 genes for predict as OGs. This is the recall. If we choose another 0.05 false positive rate, we get 451 OGs, and this is the recall. Okay, so finally, I'm going to do another analysis for using a subset of features specified by Jed. He gave me those subsets of features because we want to examine how well the prediction or classification would work if we just use a subset of features that are biologically reasonable. And we want to compare this prediction performance, their prediction performance, to what we got, so we can argue that using all the 75 features, we can do better. So I'm going to load those feature subsets specified by Jie. So you can see they correspond to mutation features, genomics features, phenotype features, epigenetics features, and without mutation, without genomics, without phenotype, without epigenetics, CRISPR only, and TOS-on, TSG, and all. So we're just going to compare everything. Okay, and what I'm going to do is I'm going to compare the precision recall curves for of every subset. So every subset will give me one curve, and I'm going to compare those. So in this case, I've already chosen the elastic net. So I'm going to apply elastic net to train based on a subset of features and then do prediction. And then I'm going to obtain the predicted values. And then I'm going to use the PR curve function as before. We've already seen that. So let me just run this chunk of code. And actually, everything is saved here. So I saved everything. I create a folder called intermediate output, and it's in our data. So let's say if we want to save us some time, I can directly load this R data. So I don't need to run everything right now. Okay, and we can check the results. So this is the PRAUC values I got for every feature subset: mutation, genomics, phenotype, epigenetics, and everything. So this is what we got using all 75 features, the highest one. But you see that if we remove epigenetics, it drops a lot. So this suggests that epigenetics is a very strong features. If we look at their own prediction, we can also see that, right? Mutation and epigenetics are the two groups of features that give us the highest AUPRC. So this result justifies our rationale in DORGE, that is, including epigenetics is very useful for predicting TSGs. And I'm going to do next OGs. So everything is just similar. I don't need to repeat everything I did, but I'm going to just show the results again. Load. And let's take a look. So this is for OG prediction. And in this case, the effect or the contribution of epigenetics is smaller, not as much as TSGs. Mutations is the most important one. Okay, that's the conclusion we did. And also one more thing I want to point out is that, as our paper said, the CRISPR-only feature is not a very strong predictor, in contrast to some people's belief. And if we go back to the CRISPR for TSG, also not very strong. Okay, and one more thing is that I wanted to obtain, so for two feature subsets, I want to obtain their predicted probabilities for TSGs and OGs. And this is what Jie will need in his paper. So he will need this result. And also, I think I made a mistake here. It should be 3, right? Because there are 3 subsets. And one more thing I want to say is that after discussing with Dr. Wei Li and Jie, we decided to use this 0.01, that is 1% false positive rate, as our targeted false positive rate for choosing the threshold. So all the results in the paper are based on this FPR. And so if I want to, let me see. So I think I can skip this part, because essentially I'm just repeating everything I said just for those 2 feature subsets and save them to some files. All right, so this part can be folded. And next thing is a very interesting part I want to share with you is the clustering. So we want to examine the feature importance. However, a contradiction we faced is that since the features are highly correlated, then their marginal contribution cannot be consistent with their conditional contribution given other features. So for example, a feature by itself may seem very strong if we just use it for predicting the class labels. However, if there's another feature that is highly correlated with this feature, putting them together into the model, then the conditional contribution of one of the 2 features will become smaller. So how do we address this? Because to biologists, they are not buying the argument that the more features I add, the weaker the features become. That seems counterintuitive. On the other hand, they also don't think marginal contributions are good measures of the feature importance, because we are not using marginal features for prediction. We're using them together. So how do we address this dilemma? I couldn't find an ideal, or I will say systematic solution yet, because I think I need more research to really think this through. But I did a preliminary try in this analysis. So my idea is that I want to cluster my features into feature groups. Hopefully the features within a group are highly correlated, while the features between groups are almost uncorrelated. In that case, I created uncorrelated feature groups so that the contribution of those feature groups can add up. Their marginal contributions are not really overlapping. And also, I can use the feature importance of that group to represent all the features within the group. So that can make my interpretation much more easily. So in other words, I'm going to talk about feature groups instead of features, starting from this point. So I performed hierarchical clustering on the gene correlations, on features, my bad, on features based on feature correlations. So you see that I'm calculating the correlation. I take the absolute value and I do 1 minus the absolute value as the distance. Okay, so which means that the smaller the absolute correlation, the bigger the distance. Then I do hierarchical clustering. So you can take a look at this H-class function, and you see that the default is to do complete linkage. So what does complete linkage means? It means that I actually require my features to be in one cluster if all the pairwise distances within that cluster are below my threshold. So for example, if I cluster them at the threshold distance 0.01, it means that all the pairwise correlations must be great within the cluster must be greater than 1 minus 0.01. That's the 0.09. So I did complete clustering, and I look at how the cluster merges. So you see that I'm showing the merging thresholds in my hierarchical clustering tree. And you see that most merges occurred between 0.9 and 1. That means what? That means it's reasonable to cut the tree here, because after this distance, there will be a lot of merging, while before that, the merging is very few. So there's a clear change point here. And I decided to do that. And you can see how many groups I got by this approach. So I did cut tree, and I can show you how many groups I got, and that's 20. So I got 20 clusters of features. And this loop is just going to show you the features. So you see that for the 20th group, I got those features. And for the 19th group, I got those features. 18, those features, 17, one feature, this. And so you see that I showed this result to Dr. Weili and Jie, and they think this partition of features seems reasonable. So it seems that indeed, features that are supposedly to be similar are together in one group. So I'm going to use this. And this also makes sure that since I'm cutting at a distance 0.9, so which means that within each group, the pairwise correlations must be at least 0.01. And then between those groups, we don't have correlations larger than 0.01. So that 0.01 seems to be a very small correlation already. So this can guarantee that my groups, between groups, the correlation is very small. That's the rationale. Okay, and then what I did is that I tried to evaluate the group importance, use the same criterion we used before. That is the precision recall area, PRAUC. So using this, what I did is that I leave one group out at a time, and then I use the remaining features to fit the elastic net, and I use the 5-fold cross-validation PRAUC to evaluate the performance. I have to use cross-validation to avoid overfitting. Otherwise, the more feature, the better the performance. So in other words, this is called leave one feature group out, cross-validate, leave one feature group out, precision recall curve. So I'm going to just run this, and you see I'm using parallel computing for that. So let's do it. And this will show how much reduction in PRAUC I would have by leaving that feature group out. So I'm putting all the feature groups on the same ground and evaluate their performance given the other features. So this may take a little time to run, but hopefully we'll finish soon. And then I'm going to show the PRAUC based on all features minus the PRAUC by leaving that feature group out. So this difference will give me the reduction, and this reduction will reflect the importance, right? The more reduction we have, the more important that feature group is. Oops, PRAUC all. Sorry, I forgot to run this one. CV, TSG, LR, ElastiNet. Sorry, I think maybe because I skipped that part in my code, I didn't run it. So here it is. So let me just spend a little time to run this one. And I think I also need to run that, the corresponding one for the OG. Okay, and I'm going to scroll back down. Oops. And OCVOG index. Sorry, I think I skipped too many things, so that's why it didn't run, but CVOG. Okay, yeah, I need to run this part first. Oops. All right, and then I'm going to rerun this part. All right, so now let's take a look at here. So this one will be okay, and this one will be okay. So now you see, looking at the reduction, clearly the reduction is the biggest for group 19. And group 19, in other words, contribute the most to the prediction of TSG. And what is that? We can order the groups based on their contributions. So this is the output. Group 19, the most important one. And based on our rationale, it's what we expected. This is the epigenetic feature group. It made the biggest contribution to the prediction of TSG based on the criterion we set. And the second one, so if we see there's a big jump, right, from 0.07 to 0.007. The second one is those things. And the next one is the missense mutation. So this is what people usually believe to be very, very important. But now given the other features, now we see the order is no longer the same as the marginal contribution. So probably this one is the strongest one in terms of marginal contribution, but given other features and because of their correlations, it's not as important as the epigenetic one. So which means the epigenetic feature make very unique contribution to the prediction of TSG. And we're very happy about that. And so we decide to set a threshold on the contribution to 0.005. So using that threshold, feature group 4, 11, and 19 will be reported as important features for TSG prediction. And for OG, I did the same thing. So I'm just going to run everything and we'll just wait a little bit. Okay. So while waiting for this, I'm just going to say what I did finally. That is, after I obtained the important feature groups, let's say feature group 19, I'm going to marginally rank features within that group. So the idea is that within that group, every feature is highly correlated with one another. So given that, looking at their conditional distribution may not seem very reasonable, but instead we can look at their marginal contribution to see among those highly correlated ones, which one is marginally the strongest. So that's my final part. And we can take a look at here. So what I did, how do I rank it? Is actually I'm using the Wilcoxon test, 2 sample test. What I did is that I compare one feature value between TSG and NG, and I ordered the feature marginally by its Wilcoxon p-value. Okay, so let's look at the OG result. So this is the figure. You see, in the OG, we have some strong groups. Here, 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 and here, right? So if I look at those 5 groups, the first one, group 4, which was this one. So it's actually missense mutations. That's the strongest features. And then we have this early replication timing super enhancer. That's group 12 right here. And then group 2, another set of mutation features right here. And then group 14, this is regarding some epigenetic features, hypermethylation. That's this one. And then the 5th one, group 20, this one, it's actually about some other histone modifications. So we still see that for the OG prediction, even though epigenetic features are not as important as in the TSG prediction, but still they're among the top 5 groups. Okay, so finally, we can take a look at the marginal ranking. So I'm just going to quickly show that for each of the top 3 groups for predicting TSG and each of the 5 groups for predicting OGs. So, all right, so let's look at the results. So top feature groups, I think I may have missed it somewhere, but I'm going to rerun it, sorry. TSG, OG, I think I missed that line. Okay, so top feature, okay, I didn't run this line, sorry. And let's go down here and I'll rerun this chunk. All right, so looking at the TSG, you see, I have top 3 groups, and this is the ranking within group 19. So we see that this mark is very important. Its height and its length are both very strong predictors. And also this mark as well. And in particular, I think your group is mostly interested in this mark, right? H3K4 trimethylation. And even though it's not ranked the top within this group compared to other features, but its own p-values is still small enough. So we can still say it's a very strong feature. Okay, and this is the ranking for group within group 11, within group 4. Okay, and that's for TSG. For OG, we also did the same ranking for every feature group. And if we scroll down here, we can see that for the feature group 14, this is what we got. So we can use those marginal Wilcoxon p-values to evaluate how strong that feature has distinguished the TSGs from NGs or distinguishing OGs from NGs. So that's all for what I did for my part. And then a lot of my results were sent to Jeff for his plotting.